is no difference between learning and inference if you are thinking in terms of Bayesian learning. That's what we are talking about, right? Anyone?
Because it uses inference and the conditional probabilities given to learn the new ones?
What?
Is it because it uses the conditional probabilities and inference to learn new probabilities or something?
Not really. Yeah? Did you want to say something? No? Who wants to say something? See, we are supposed to have discussion classes once in a while. And apparently discussion class would be kind of quiet. So. Anybody? I mean, is anybody at all surprised, first of all, that there's no difference between learning and inference in Bayesian view? This takes forever. And you know, you guys should start paying a little higher tuition so that we can actually get computers here as against things that pass for computers. Okay. Yeah, so does this remind anybody anything? So either we are having extended spring break or people have realized that half the semester is over, we should change classes. So maybe they thought that this is one of these half semester classes. I don't know. So we were looking at Bayesian learning previously in this class before you went off for spring break, and statistical learning, and we essentially thought that all you really think of in learning is you basically make a hypothesis that explains the data, and you probably have some sort of a prior on the hypothesis. There could be many different hypotheses. You have a prior on the hypothesis, and then you look at the data. The hypothesis causes the data in some sense. And so given the data, given the hypothesis, you can compute the likelihood of the data. So it's easy to compute PD given H. Okay, and what we really need to do is compute the posterior. So there's a prior on the hypothesis, and you can think of learning itself as essentially a Bayesian network. So the hypothesis is an extra variable on top of the data variables. Here the data is shown as just a single variable, but it could be multiple variables. Like for example, your the burglary earthquake scenario could be a little network in each of these places. Okay, and each hypothesis, for each value of the hypothesis, you can compute what is the probability that this data will be observed given this hypothesis. Okay, because that's part of what you have here. Okay, and if you see a whole bunch of data, what you're essentially trying to do is use the Bayes rule to compute the posterior on the hypothesis given the data. Okay, and that is essentially the posterior distribution of the hypothesis given data is proportional to prior distribution of the hypothesis times the data given hypothesis, which is this part. So data given hypothesis is typically called the likelihood of the data given this particular hypothesis. Okay, now notice that actually this is a distribution. You're talking about distribution of all the hypothesis variable. Okay. Okay, so that's basically what we can do, and so in essence, there is no difference. So once you get the posterior distribution of the hypothesis, then you know which hypothesis is more likely and which is less likely. And in predicting the next data, all you really need to do is you do a weighted prediction. You know, the probability that the data would be this, given this is the hypothesis, times the probability of the hypothesis itself, given all the past data. Okay, that's what we went to in this example. And basically here, this was the prior distribution of the hypothesis, and these are the posterior distributions of the hypothesis as you saw more and more data. Okay, and then at any given point of time, if I say stop now and try to predict the next data, okay, you can do that essentially using weighted prediction of hypothesis. Okay, and that's the prediction here. And we notice that the prediction correctness will, as the amount of data that you have seen increases, the prediction accuracy becomes 0.0. So in some sense, this is considered, as I mentioned last time, this is considered the optimal way to do learning. Any other learning algorithm ultimately would be compared to Bayesian learning. Okay, the problem with Bayesian learning most of the time is essentially, in some sense, you are not making up your mind at all as to, there is no learning in Bayesian learning, right? Because you're just keeping track of all the hypotheses and you're just changing the distribution, the likelihood of those hypotheses as the data keeps increasing. Which is easy enough in this in this little example, because there were only 5 hypotheses. What if you have 20 hypotheses? What if you have infinite number of hypotheses? In fact, it's easy to get an infinite number of hypotheses. So for example, if I'm trying to figure out that, if I'm trying to essentially say that the probability that when I pick the next candy, it would be cherry candy is theta. Now I'm trying to figure out what is this probability theta. That's a probability number between 0 and 1. How many possible values can this take? Infinite number of values. It's a continuous hypothesis space. Okay, so you can do Bayesian learning there too, except then you essentially have to maintain the posterior on the continuous hypothesis. Okay, so chronologically, what happened is basically people start from here and start simplifying their life and say, rather than actually compute the entire posterior distribution of the hypothesis given the data, I will just try to find the mode of the posterior distribution. Remember what the mode is? It's the value for which the distribution is the highest. The probability is the highest. Okay? So find me, if you notice, this is the distribution that we were looking at. The distribution we were looking at was of this form. This is how you computed the posterior. Okay? Now the question is, what is the value of HI for which this component would be the highest? So this is the probability would be the highest there. Okay? And then I will assume that that's the hypothesis I'm going to pick. Rather than assume, this hypothesis is this much likely, this hypothesis is this much likely, I will pick one winner. And the winner I will pick essentially by looking at the place where the posterior is the highest, the hypothesis for which the posterior is the highest. Okay? Then that's the basic, that's the first idea. That's called the map approximation. So essentially you are going to compute the hypothesis for which this product is the highest. Or you want to pick the hypothesis for which this sum is the highest. Because if you're trying to pick the hypothesis for which this product is the highest, it would be the same hypothesis for which the log of that would be the highest. And the log of that would be, can be written this way. Right? Okay. Now the interesting thing about this is this kind of nicely splits into one part which is sort of log of the likelihood. Remember, D given HI is considered the likelihood. So you consider log of the likelihood plus log of the prior. Okay, now this is basically what, and so log of the prior is how likely is the hypothesis to begin with, even without having seen any data. Okay, and then this is how basically how likely is the data given that hypothesis. Okay, so this will ensure that you won't come up with the most complex explanation to fit the data. Do you see what I'm saying? You know, what was the example I used last time? I mean, there are many examples you can use, but one example I used to illustrate this was you could explain some of the observations of what's going on in the seasons on Earth by either positing a very complicated planetary motion with Earth in the middle, okay, or a simple planetary motion with Sun in the middle. Okay, and both of them will agree with the data. But the assumption is this part would be higher for Sun in the middle and lower for Earth in the middle, because that's a much more complicated hypothesis you came up. This is also connected to what's known as Occam's razor, which is find simple explanations to explain the data. Okay, so that's basically what is being captured by the prior of the hypothesis. Okay, and then this is, as I said, this is the scientific method in general. This is how you pick one hypothesis that is the that explains the data. Okay, now one interesting thing, of course, is this essentially requires that you need the prior on the hypothesis itself. Okay, and some people don't like having any kind of priors on the hypothesis. So those of you who you have done physics, quantum physics at some point of time. Did you do quantum physics at some point of time? So if not, at least you must have heard this thing that Einstein was against quantum physics. He felt as if that all these probability numbers don't seem to make too much sense. There shouldn't be too much uncertainty. And so, he used to go around saying that God doesn't play dice with the universe. And then Niels Bohr would tell Einstein, don't tell God what to do. Right? So the way to understand that is Einstein had a prior as to what essentially would be likely hypothesis governing the universe. Okay, and Niels Bohr was saying, I don't want you to have any biases. I want you to just see the data and try to come up with the most likely explanation for the data. Okay, one of the interesting things is actually this also brings us to an interesting dichotomy. Remember a while back when I mentioned Bayes' rule, I also mentioned, I think I discussed about the fact that there is a distinction between statistics as frequencies, at the asymptotically, a probability as essentially a frequency experiment, okay, or probability as something that you just made up, personal probabilities. Remember I talked about this, okay? And I said the personal probabilities are Bayesians. Bayesians say you can make up your own probabilities. All we want is you be consistent with the probabilities you have. Okay, so Bayesians think it's completely fine for you to assume that there is, the probability that you will get mugged on Mill Avenue as you're walking is 0.9. Okay, and it's also completely fine for you to assume that the probability that you'll get mugged when you're walking on the Mill Avenue is 0.001. So maybe this person will assume 0.9, this person will assume 0.001. I don't care. All I would do is if this guy assumes 0.001 and he's going around with a bulletproof vest on Mill Avenue, I would say, why are you doing this? You don't believe that you will get mugged. Why are you taking all these precautions? You're not being consistent with your own beliefs. You see what I'm saying? That's what Bayesians say. Okay? So the interesting thing is that Bayesians essentially want, basically say that you can make up your probabilities, and as pure statistics, the frequentists say you cannot. And frequentists also tend to say that you should not have any biases about what the final hypothesis is going to be. You should let the data tell you what the hypothesis is. So the statistics, the frequentists would say, we don't like this at all. You have a prior. So in fact, Niels Bohr is being a frequentist when he told Einstein to shut up and stop telling God what to do. Because he's saying, you should just only look at the data. You shouldn't look at the prior. You shouldn't make up your mind as to the, what's the distribution on the hypothesis. In fact, in frequentists, some of you have taken, any of you have taken AP statistics at some point of time, or some actual statistics course? Okay, so much of what I'm doing, you have done it in a different way in AP statistics, because most of you who did AP statistics would have done frequentist version, where you do not think hypothesis is a random variable at all. Hypothesis is an extra statistical variable. You cannot say given hypothesis. If, for example, you say probability of D given hypothesis here, right? That's very Bayesian thing to do. The correct notation that frequentists use is probability of data semicolon hypothesis, right? Because hypothesis is not supposed to be a random variable. And if it's not a random variable, you can't have a distribution over it. Now you'd think, what's the big deal? This seems to be somewhat, bunch of syntactic rivalry. But man, there is a huge deal in statistics community between Bayesians and frequentists. And for the longest time, actually frequentists basically ruled the world in their little statistics world. And now Bayesians are ruling the world to some extent. Or at least they're still also getting faculty positions in statistics departments. In the past, if you want to say, I think hypothesis is a random variable, they'll say keep moving. Don't stop at the statistics department. Okay? So it's one of these big philosophical debates. And so that you sort of stumbled into. We don't care about it in this class because we came sort of from the Bayesian angle. Okay? So up until this point, actually, frequentists will be kind of rolling their eyes up, saying, what's all this you're doing? You're being influenced by something other than the data, because you have made up your mind as to what's likely hypothesis before looking at the data. Now, one more approximation you can do here is if the data is humongous, there's a large amount of data, then eventually this term will dominate this term. So, when you have large data, that means you have humongous amount of training data, then you do not actually need to have a prior on the hypothesis at all, because eventually this will dominate this, and so you may as well just pick the hypothesis that maximizes this single term. Do you understand what I'm saying? In the large data case, map and in large data case, so this is called the map approximation. A different approximation is called the likelihood, maximum likelihood approximation, which only maximizes this part. It doesn't care about this. And it turns out maximum likelihood and map do the same thing for the large data case. Because when the data, you have large amount of training data, then eventually this will dominate this. So it doesn't really matter what biases you started with. You see what I'm saying? Now, in physics, maybe doing, a reasonable experiment to actually check whether or not something is true will take $3 billion. Right? Okay, so do you guys know how long it took for the first experimental evidence to come for Einstein's theory of general relativity, for example? He came up with it out of, whole cloth. Because this man is made up of all sorts of biases, and he came up with it. I think that's how the world will work. And then it took a while before people actually figured out that light actually does bend. Okay? So the training data comes not all that often. So science tends to be the small data case. So saying I only go with the data wouldn't get you anywhere, because you will tend to make all sorts of pseudo-scientific hypotheses, such as all sorts of pseudo-scientific explanations, such as palmistry, that is your life is based on what's written on your hand, or phrenology, it's based really on what's written on your head, and so on and so forth. And all of them will sort of agree with 2 or 3 cases. You see what I'm saying? I believe in palmistry because, the one guy I know who had this little kink in that did actually die at 35 by being, hit with a large bulldozer. And so pretty much that is explained right now. Do you see what I'm saying? So in small data case, it's actually, you need to have a good prior on the hypothesis. Otherwise, any random thing can explain a couple of observations. In the large data case, basically you don't need the prior. So just as science is more like a small data case, in some branches of science, learning from recommendations on the web, learning stuff on the web, for example, tends to be much more of a large data case. Right? And so in those cases, essentially, there is no difference really between map and ML, and you essentially just go with ML. Okay? Now the interesting thing is if you come to ML, we came to ML in this class by first saying, we came to ML in this class by first saying that this is the right thing to do, okay? And that, but it is too hard to do, so then we'll do this. That too is kind of hard, we'll just do this. Now, when we come to ML, then our frequentist friends will say, now you're talking. Now you are not being biased, because you have no prior biases about hypotheses. So we'll talk to you. Okay, so for the rest of the class, we actually assume that ML approximation is done. That means you do maximum likelihood approximation. That means pick the hypothesis that maximizes the likelihood of the data. That's all. And it has all sorts of pitfalls. You can once in a while pick, in today's class itself, we'll see that if you're not careful, you can pick hypotheses which won't make too much sense, even though they agree with the data. Okay? But it works, in some of the cases, and it in fact is the simplest idea to go forward with. And if you come to this from the frequentist statistics, from the AP statistics point of view, then both you and I would be happy. I mean, both Bayesians and frequentists would be happy for this, for just different reasons. Okay? Okay, so that's a summary, essentially, of what we did last class. Okay, so now what I want to do is actually do an example. Remember what I want to do essentially is learn Bayes networks from the data. That's how we got into this. Okay, so I want to learn basically Bayes networks from the data, and my simplest case I'll assume is I have a single node Bayes network. Okay, the single node Bayes network, the node is flavor, that's it. And the flavor is cherry with probability theta. That means it's lime with 1 minus theta probability. This is my hypothesis as to what the data is going to be. Now, for each value of theta, I have a different hypothesis. Theta equal to 0.0001 is hypothesis, one hypothesis. 0.00011111 is a different hypothesis, and so on. So there are infinite number of hypotheses right now. Okay? And what I can do is I can compute the likelihood of the training data that I have seen given each of these hypotheses, given the hypothesis as the variable. Okay? And then find where it becomes maximum. Remember, I want to just maximize the likelihood. So if I can somehow compute the likelihood as a closed form function and find the maximum of it, and now we are talking about continuous functions. So you have to remember your calculus. If you want to find the maximum of a continuous function, what do? You take the derivative and equate it to 0. Okay? And if you are lucky, you will be able to solve that equation. If you are unlucky, that equation would be probably a set of simultaneous equations, because if you have multivariable function, then you are setting multiple partial derivatives all equal to 0. So you have a set of simultaneous equations, and then these equations don't have to be linear. They can be non-linear. So if you're unlucky, you will be solving a set of non-linear simultaneous equations to find the optimum. So this is function optimization. This is search in continuous domains. The search that we did in the beginning of this class is search in discrete domains. It's called combinatorial search. And the one that we are interested in this particular part is the continuous search. That means finding the optimum of a continuous function. Okay. Now, thankfully, for the first two examples I'll see, you'll notice that actually the partial derivatives will all become simultaneous equations where each equation is about one single variable. So that means they are simultaneous equations where each equation, the first equation is only about x1, second is only about x2, third is only about x3. Okay, so they're not really simultaneous. Okay, and furthermore, they're all linear equations. So it should be very easy to solve them. You'll see that happen. But in general, you can have the harder case. Okay. So let's go through the steps here. So I have, this is my family of hypotheses. This picture tells me an infinite family of hypotheses. Does everybody see that? Because for every different value of theta, I have a separate hypothesis. Okay. Now what I'll do is suppose I have seen C number of cherries, cherry candies, and L number of lime candies, total. Okay, so that means I got, cherry, 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 lime, cherry, cherry, lime, like that. And if you count all the C's, it's C number. All the cherries, the total number is C, and all the limes, that total number is L. Okay, now since basically then what I want to do is, since all the data, one of the interesting assumptions we always make is all the data, the picture that we have is all the data is independently generated by the hypothesis. So given the hypothesis, the data is independent of each other. Okay, so to compute the likelihood of the data given the hypothesis, I'll compute the likelihood of each data piece given the hypothesis and multiply all of them because they're all just independent. Okay, now if I saw my first candy was a cherry candy, then what's the probability of that happening? Theta. The next one is a lime candy. What's the probability of that happening? 1 minus theta. So the probability that I get one cherry and one lime is theta times 1 minus theta. Now the next one is another cherry. So that's again one more theta. So it will become theta square. And one more lime. I'll get 1 minus theta square. So if I have a total of C cherries and L limes, then my total probability of finding a sequence of C cherry candies and L lime candies, okay, is theta power C times 1 minus theta power L. Right? This is a continuous function. It's a function in theta. It's a function in theta. And this is also a function of how many variables? What? It's one variable function. Even though I made a huge deal about multiple variables, this is the simplest case. This is a single variable function. So if you want to optimize this function, all I need to do is I take normal derivative, not the partial derivative, just normal derivative of the function with respect to theta. Okay. Now, rather than directly optimize this product, what I'll do is I'll optimize the log of this because it's sort of easier to optimize that function. And log is monotonic. Log monotonically increases. So if the log of a function becomes optimum at, let's say, point P1, then the function also becomes maximum at the same point P1. The values will be different, but all I care about is where does it become optimum. Right? So I'm taking the log of this. I will get, basically, what will I get? I'll get log of this whole thing, that is C log theta plus L log 1 minus theta. Right? Now if I differentiate that, So C log theta plus L log 1 minus theta. If I differentiate this with respect to theta, and if you remember your differentiation, right, I'll get here, so C log theta will be C by theta. And L log 1 minus theta would be minus of L by 1 minus theta. Because you think of 1 minus theta is u, so log of u will be 1 by u, so L by 1 minus theta, and then you have to differentiate 1 minus theta once again to get minus 1. So you put that minus 1 here. Right? That is equal to 0. You want to equate that to 0 to get the maximum value of this function. Okay? Actually, all you will get if you set it equal to 0, you will get either a maximum or a minimum. And then you're supposed to do the second derivative test. For now, we won't worry about it. Okay? So anyway, you set it equal to 0, then I can compute from this, I'll get a simple equation, theta is equal to C by C plus L. So what did I say? I said, if you have seen till now, in the training data, you saw 15 cherries and 20 limes, then the probability that you will get cherries is 15 by 15 plus 20. That's exactly what you would have done if I didn't tell you anything. But right now, you have math behind you. You have an actual reason as to why you're doing what you're doing. Do you understand what I'm saying? Okay? This is what you would have done. If I said, I seen 15 cherries and 20 limes, what do you think is the probability that the next one would be a cherry? You will say, yeah, it's 15 by 15 plus 20. But that's because you essentially had some sort of assumptions you made. First of all, you assumed all hypotheses are uniformly likely. By the way, one other interesting way of thinking about ML with respect to map is that either you can think of ML as map in the large data case, because this term then dominates this term, or you can think of ML as map with this term being, the prior being uniform. That means all hypotheses are uniform. In which case, for every hypothesis, you will add the same exact number. So it doesn't change anything. Do you see what I'm saying? Not knowing anything is like assuming they're all equally likely. So both are useful ways of looking at it. Okay. So I got theta equal to C by C plus L, or basically C by the total number of candies. And if you do that, then the log likelihood would be maximized. Okay, so now I've just learned a Bayes network of one node, okay, where I was able to get the theta value to be based on my training data. Okay, this is as good as, it's okay, but in fact, if the data is small, if I just saw right now 2 candies and they both happen to be lime, then by this argument, what would I say? The probability of cherry is 0. Would you believe that really? No, because you realize that the data is small. Okay, one issue is what to do. What to do if you think the data is small and you really don't want to jump to the conclusions. One idea then is, of course, this problem wouldn't have happened if you had a prior on the hypothesis. But we don't want to do that. So another way of doing it is assume virtual data. Act as if in the beginning, okay, in the beginning you have seen 2 limes and 2 cherries to prime the pump. Do you see what I'm saying? Just assume you've seen 2 limes and 2 cherries, or at least 1 lime and 1 cherry to prime the pump, so that nothing ever becomes 0. Now, if it turns out that really, you are deluding yourself when you made this virtual assumption, and in fact, the next million candies were all limes, you will basically find out that the lime probability is 0.9999999999999, or the cherry probability is 0.0000001. So you will get effectively the same, performance. But you have avoided the problem of assuming that I should never be seeing a cherry just because I saw 2 lives in my small example data. Do you see what I'm saying? And that is essentially called, in fact, let me go there and show that to you, if I can. I'll come back to that in a minute, but that's called smoothing. That's called smoothing. And this is also called Laplacian correction. Okay, so the need for smoothing is, if in fact the data is small, then certain possibilities may not have happened in the data, and so you will set them to 0, those probabilities to 0. And the zeros are problematic in probabilities. 0 multiplied by everything is still a 0. 0 multiplied by infinity, close to infinity, is still a 0. So you will never ever learn anything new. Okay, so to avoid that, what you will essentially do is you you wouldn't have gotten into this problem if you had done Bayesian or map. You got into this problem only because of ML, and ML only makes sense if you have large data. Right? And so you just suddenly realize that you don't have that large data to begin with. Okay? So then basically you sort of make virtual samples and add them to the denominator as well as the numerator, so that you'll never get zeros. And as the real data increases, the effect of the virtual data dies out. And that's called the smoothing. Okay? And I kind of like that code. It's apparently Oliver Cromwell, for those of you who might remember European history. If you have done AP statistics and also AP European history, then you might know Cromwell. And he apparently told the church, I beseech you in the bowels of Christ, think it possible you may be mistaken. That's exactly what you're doing. Think it possible that the data that you have is probably not a fair representative. And so you are hedging your bet. So that's how you deal with the 0 counts. Okay? Yes?
Aren't we actually putting the prior in another form?
Yes, it is. So the reality is, as I said, this is why this discussion is extremely important for you to understand if you want to have a true understanding of what happens in statistical learning. You have to realize that you're doing this either because you're intellectually lazy, because you don't want to do the full Bayesian learning, or because you think the data is large enough that the priors don't matter. When the data isn't large enough, then the priors do matter. And all I'm saying is, some of you may have seen this kind of smoothing idea. This, if you have heard of naive-Bayes classifier, which we'll be mentioning in the next 10 minutes, okay? You do that in naive-Bayes classifier. And the reason for that is essentially bringing back or relaxing some of the assumptions you made. You made assumptions to get here, and those assumptions may not always hold, in which case you add these virtual counts. Yes?
But what if your large data is also biased?
Yes, that's why you always, basically what you do, it's the smoothing is a poor man's way of not getting stuck into a corner. If you really want a clean way of not getting stuck into a corner because of biased data, you have to either do map or better yet to do Bayesian learning. And despite the fact that here I made it sound as if Bayesian learning is a monster, mathematical monster, actually, if you read machine learning literature right now, there's a lot of work being done directly on Bayesian learning. The textbook actually has like one section on doing direct Bayesian learning, even with continuous parameters. I just don't want to go into it here because it probably would be a more reasonable thing to do in the next course. Okay? Any other questions? Okay. So now the next thing I want to do is, so this people understood, right? I just went through the motions to come to a point that you kind of guessed beforehand. But the motions are important because that is what is giving the theory as to why you are allowed to do this. Okay. The next thing I want to do is actually just do a slightly longer example of this, which is now I have a 2-node Bayes network, which sort of at least looks like a real network. That one looked like, 1-node network doesn't look like a network at all. Okay, so For the two-node Bayes network, here essentially I have flavor and I have wrapper. Okay? And so essentially my generative model for this data, my hypothesis is that the manufacturer sort of with some probability theta picks either a lime or a cherry. So with probability theta he picks a lime, a cherry, and otherwise he picks 1 minus theta he picks a lime. And then having picked one, then with a probability, if he picked cherry in the first step, with probability theta 1, he will put a red wrapper on it. Probability 1 minus theta 1, he will put a green wrapper on it. So once in a while they want to mislead you, so that you will still buy, a candy which is red wrapped, thinking that it'll always be cherry, but sometimes it's lime. And similarly, you might be buying, green wrapped candy and find there's a cherry. You see what I'm saying? So that's my new model. Okay? So the data for this would be, remember always the data would be attribute value, attribute value. Previously the data was flavor equal to cherry. Flavor, then that's first example. Flavor equal to lime is the second example. And then maybe flavor equal to cherry is the third example. Flavor equal to another cherry is the fourth example, and so on. Now in this, my data would be flavor equal to cherry, wrapper equal to red. Flavor equal to cherry, wrapper equal to green. Flavor equal to lime, wrapper equal to green. Flavor equal to lime, again cherry maybe, wrapper equal to red. That could be my data. These are the observed data. Okay? From this, I want to figure out for what values of theta, theta 1, and theta 2 would I get the maximum likely hypothesis. That is the hypothesis that maximizes the data, maximizes the likelihood of this data being generated. Maximizes the likelihood of this data being generated. That's what we are doing, right? So once again, all I need to do is if I have this Bayes network, theta, theta 1, theta 2, what is the probability of this particular data point? Probability of this would be, the flavor is cherry, that means capital theta. And wrapper is red. If flavor is cherry, wrapper would be red with theta 1 probability. So it's theta times theta 1. Right? And then this would be theta times theta. What is this? Exactly, 1 minus theta 1. And this would be 1 minus theta times 1 minus theta 2. Right? And then this would be theta times theta 1. Right? Now all these 4 samples have been seen independently. So the probability that I would see all of them is this times this times this times this. That would get me essentially, in this case, theta cube 1 minus theta, right? Theta 1 squared, 1 minus theta 1, 1 minus theta 2. Agreed? I just did the numbers, basically I just crunched the expressions. In general, if I saw C cherries and L limes, I would have a theta power C and 1 minus theta power L in my expression. And then of the C cherries, if RC were red and GC were green, then I will have theta 1 power RC and 1 minus theta 1 power GC. And similarly, of the limes, if RL is the red limes and red wrapper limes, and GL is the green wrapper limes, then I'll have theta 2 power RL and 1 minus theta 2 power GL. Okay? Right? So, understand this part. You always have to, based on your Bayes network configuration, you need to write the expression for the data likelihood. Once you do that, everything else is just function optimization. So you need to understand this is the likelihood of the data where I have seen C cherries, L limes, RC of the cherries for red wrapper, GC of the cherries for green wrapper, RL of the cherries, RL of the limes for red wrapper, and GL of the limes for green wrapper. And if this is what my hypothesis is, the probability that I would have seen that data is this expression. Okay? Now, if I take the log of that, the log likelihood is C log theta plus L log 1 minus theta plus RC log theta 1 plus GC log 1 minus theta 1 plus RL log theta 2 plus GL 1 minus GL log 1 minus theta 2. If you think this is ugly, it's not. It's quite beautiful. Why? Because what are you going to do now? First of all, this is a function of how many variables? 3 variables. If you want to find the maximum for this function, you still need to get the derivative and equate it to 0. But what's the derivative here? You have a partial derivatives. So your total derivative is made up of 3 partial derivatives. So you need to make the gradient vector equal to 0, or essentially each of the partial derivatives must be set to 0. That will actually give you, thankfully, 3 equations with 3 unknowns. And you just have to solve for the unknowns. As I said, without actually doing it, you don't quite know how crazy those equations could be. First of all, they could be simultaneous, in the sense each equation mentions all the unknowns. And second of all, each of the equations can be nonlinear, and so it could be pretty painful to solve them. But luckily for you, for this case, what do you think will happen? If you do differentiation with respect, partial derivative with respect to theta, this goes 0, this goes 0, because this doesn't depend at all upon theta. This doesn't depend at all upon theta. Only this will depend on theta. And this looks very similar to this, right? Okay? And so, essentially, you will basically find that this would be C by C plus L when you set that equal to 0, okay? Actually putting all 3 equations, dou L by dou theta would give you theta to be C by C plus L, dou L by dou theta 1, the partial derivative with respect to theta 1 would give you this expression, which should be equal to 0. That means theta 1 is RC by RC plus GC. And similarly, theta 2 is RL by RL plus GL. Are you surprised? Again, you are not surprised, because this is what you would have done if I didn't drag you through all these partial derivatives. But now you know why you're doing it, right? I mean, the difference between a computer science person and a hacker is a hacker just kind of looks at a library and picks one function and starts using it, and assume that somebody knows why it is right, okay? And if it fails, somebody else will tell me why it is not working. And hopefully you will know before using a tool when it is supposed to work, when it's not supposed to work. Okay? So this is essentially telling you that you are actually right in assuming that setting the wrapper, the probability of theta 1, this probability theta 1 would be set as the number of times you saw red wrappers on cherry candies divided by the number of times you saw the cherry candies. It's just ratios of the counts. That's it. Okay? As much as this might look like a huge letdown, please understand that you should celebrate this, because it doesn't often happen this way. In this case, it turns out that, in fact, Bayes networks have this beautiful property that irrespective of how big the network is, okay? As long as all the CPTs are basically discrete probability tables, okay? Then the log likelihood would always be of this form, only much larger. And when you take the partial derivatives, each partial derivative would be about exactly one of the parameters. And you solve that, you get that parameter. And they'll also be linear. So you're guaranteed to be right for doing the obvious thing. This wouldn't have been the case, for example, if I mentioned during all the discussion on Bayes networks that there are other kinds of graphical models, such as Markov networks. I know some of you might remember it. It turns out that for Markov networks, this is not true. Because what happens in Markov networks is that there is a constant called the normalization constant, which just sort of ties up all the parameters together. And so when you take a partial derivative, then every partial derivative will wind up mentioning every other variable. So you get a true set of simultaneous equations, which are more painful to solve. Okay? And furthermore, if in fact these are not CPTs, but these turn out to be sort of parameterized probability distributions, such as normal distribution or Poisson distribution or something, then you are no longer guaranteed to have linear equations, you will have nonlinear equations. Okay? So it's one of these good things that happens when you do Bayes networks. Okay? And it's so good that actually it doesn't, we looked at the one node case, we looked at the two node case, it doesn't matter how many nodes are there in the network, and it doesn't matter what the configuration of the network is. So for example, if I have this as my network, this is your favorite network, burglary, alarm, earthquake, John calling, Mary calling, and the data, so I have already given myself obviously the topology of the network in this case. So the only things I'm trying to figure out is the parameters, theta 1, theta 2, and then there would be how many thetas here? 4 thetas, okay? So theta 1, theta 2, theta 3, 4, 5, 6, and then 7, 8, 9, 10. So 10 parameters. But if you actually go through the motions, they will nicely work out just the same way as the other parameters. So much so that if you have seen the data for this, observed the data, so in one case, burglary was true, earthquake was true, alarm did not go off, John did call, Mary didn't call. That's one case. So apparently Mary is calling. And then finally, and then so on. And so in this case, burglary was false, earthquake was true, alarm is true, John didn't call, Mary called. This is the kind of data you see. Right? So now if I want to figure out what should I put, one of the parameters I would need is probability of J given A, right? That means probability that John calls given alarm is true. That's one of the CPT entries I need to learn. According to my theory, I just need to count the number of data items where both John is calling and alarm did go off, divided by the number of items where the alarm went off. That's it. This is what you would have done, I understand, if I didn't tell you this. But you would have been right because of this discussion. And it's only for Bayes networks it happens. So you should be happy about that. Okay? By the way, a very interesting question is, you do know, for example, that suppose I think that the marks distribution, for this class is normally distributed. Then I need to figure out the mu and the sigma of the normal distribution. And I see marks, okay, student 1, 14, student 2, 35, student 3, 37, student 4, 89, and so on. That's data. And I have e power x minus mu, I hope I remember the expression, by sigma, and then 1 by square root of 2 pi something, by sigma here. That's the expression for the normal distribution. Given mu and sigma, I can compute likelihood of each of the data. I have to multiply all those likelihoods and set my mu and sigma to be those values that would maximize those likelihoods. Here is a nice little exercise in elementary calculus. Try to do this and convince yourself that what teachers have been doing all along was right. That in fact you are right to set, when I get this, what do? I add up all these numbers divided by the number of people. And I say that is mu. That's the average for the normal distribution. And the variance I will also compute the same way, basically xi minus xi dash square. I'm doing that, right? It turns out that's also the right thing to do, according to the maximum likelihood. The text actually has a derivation of that. And here is a case where you have, essentially, again, you have a multivariable function, and it's not a simple function. In this case, it's a quadratic function. If you take log, you will get a quadratic. Okay, and you will be able to convince yourself that what you've been doing all along was still actually correct for normally distributed variables. It's the same theory. Okay. So, learning Bayes networks seems to be very simple. It's just counting the number of examples where certain things hold divided by the number of examples where certain other things hold. And then take those ratios and set the parameters. Right? Okay? Is it always that way? What am I pushing under the rug here? I understand Bayes networks are better than Markov networks, but what am I pushing under the rug here? The first question is, who gave me the topology? Who gave me the topology? I assume this is the topology, and then I only am computing the parameters. If I just have the data, I don't know the topology. So then I have to figure out for each topology what is the best parameters, and then for each topology I'll get the best parameter value for that, and then you then set it against each other to find the best topology parameter combination. That's what you need to do. That's called structured learning. I'll see it in a minute. We'll see it in a minute. Okay? The other idea is to say, well, to heck with actually figuring out what the true topology is. I'll always assume the topology is of the following form. I'll always assume that the topology of the following is of the following form. One node here, A1, causes everything else. A2, A3, A. I'll just assume this is my topology. If you do that, you're doing naive Bayes models, naive Bayes learning. Do you see what I'm saying? Okay? And of course, naive Bayes learners would only be of all the topologies. If the topology is this, it will tell you what's the best set of probabilities that maximizes the likelihood of data. But this could be the completely wrong topology. And to really learn the new correct topology, you have to also search over topologies. I understand it's not an infinite space, but it's a double exponential space, because the number of directed graphs is double exponential. And you have no hope of doing it one topology by another topology. Okay? So this is the part where I kind of wanted to actually put this picture of people. So the easy part that I hope all of you understand is for the complete data case. So given the topology case. Okay? The other ones I sort of want to tell you what the difficulties are and kind of give you a hint of what makes life harder afterwards, but we won't go into it too much. Okay. The other issue is, so first I don't know the topology oftentimes. So if I don't know the topology, this is not true. The other is, why must it be the case that the data is complete? Remember I told you when generating Bayes networks, I said sometimes that, so first of all, the two things that could happen. Maybe the training data is such that you happen to know some of the times you don't know whether alarm went off or not. Some of the times. So I have partial data. I have data where some variables are missing values. So in a database terminology, you have null values. You have attributes with null values in some tableaus. The other possibility is that I could have an attribute which always has null value in the data. Database people won't have a column, in a relational table where an entire column is null, 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 null. But learning people have to do that. We have to do that. Why? Does anybody remember the reason why you might want to generate nodes that couldn't have been observed? Remember the auto example where we talked about state of the battery, which may not be observable, but it's an intermediate node. And the reason you put that intermediate node is it makes the structure sparse. That reduces the number of parameters you have to learn. If I only have 100 data pieces, I can't convert that 100 data pieces into million probabilities. If I do, I'll get what I pay for. You understand what I'm saying? If I blow up 100 data into million probabilities, all those probabilities that I get, all those parameters I get are likely to be completely wrong. That means it's going to be very noisy. So you want to get by with fewer parameters. And so if you have hidden variables, then essentially your data will never have a value for them. So even if I give you the topology, you still don't know how to learn, because you don't know the value for the hidden variable. In particular, when you have hidden variable, what happens is that this happy situation doesn't happen because one of the variables is missing, its value is never seen, so the observations are marginalized over the values of that variable. When you marginalize, you have to put a sigma here. You put a sigma here, you take a log, you will look very sad. Right? Log over sums is pretty sad situation. Log over multiplications is easy. Log over sums is no good. It's still the same old mathematics of optimization, except here you really need to know how to do optimization over arbitrary functions. So for example, you have to know Newton-Raphson method, where you select a point as the initial point and then try to go descending on the gradient until you find the point for where the function becomes zero. Newton-Raphson method actually is this idea of, let me see, I think I will think for it. Where do I have it? Yeah, there. So Newton-Raphson method basically says that if you have a function fx, and I'm trying to find the zero of the function, so you're trying to solve the equation. So you try to guess the value of the root of the function, that means where the function becomes zero, and then check if it is already correct, in which case you're done. Okay? If not, you essentially set the next value of x in this way. You set the next value of x to be f of x, the current value of x, minus f of x by f dash of x. F of x by f dash of x. Those of you who are looking at this carefully, you see here there is f dash by f double dash, and I'm saying f by f dash. Why? To solve equations, what you would do is f by f dash. The equation you are trying to solve is f dash equal to 0. So f is your f dash. So f dash of f dash is f double dash, which looks completely fine as long as you have single variables. If you have multiple variables, if you have 100 variables, there are 100 partial derivatives. Fine. How many double derivatives are there? 100 by 100. Right? It's called Hessian. So to do Newton-Raphson in actual multivariable functions, you need to compute this Hessian, which is a pretty hard thing to do. And so most of mathematical optimization is how to avoid doing the true Newton-Raphson method without having to essentially compute the full Hessian all the time. All of which we could avoid for our little examples because we could just directly solve the equation. This works even when you can solve the equation, but this also works when you can't solve the equation analytically. Okay, and that winds up, the reason we can't here is because I was trying to tell you trying to tell you basically this point, that as you step away from the known topology and complete data, which is what we have used till now, okay, then you can start, relax first known topology. Then you have to search over topologies. So you still assume complete data, but topologies can be different. And then the other, you can keep the topology constant as known, and then relax the assumption that the data is complete. So you will have to have hidden variables whose values are not known. So the log likelihood now will be summation, because it has to marginalize the unknown variable, the hidden variable, because that will never be actually observed by any real data. Okay? And then that makes it into a true function optimization problem. And then the third is throw away both. I don't know the topology, and I don't have complete data. Then you have to search over all possible topologies. You have to search over all possible topologies. And on top of it, for every given topology, you will need to do actual function optimization. And a version that works is called EM, or expectation maximization. That's a way of doing function optimization for probability distributions. So you can think of EM as Newton-Raphson analog for probability distributions, for log likelihoods. Okay? But I do have some time, and let me talk about how to deal with the topology issue a little more. Okay? So the problem we are talking about in the topology is, okay, sorry, it should have come this way. So if I have this data for the burglary, earthquake, alarm, etc., and you have no idea what this data is supposed to be about, you don't know whether the network is supposed to be this or any one of the networks on 5 nodes, any one of the directed graphs on 5 nodes. Okay, so what would I do? A simple idea would seem to be that I would act as if this is the topology, find the best parameters for it. I'll act as if this is the topology, find the best parameters for it. Now put these two guys. It's like a league match. It's like a tournament going on now. So the tournament for these guys, the best winner will come out of learning the best parameters for this topology. Best winner for this guy will come out with this topology, and then I'll compare both of those. How do I compare both of them? What's common? What's common is log likelihood. That is the likelihood of the data given this hypothesis. So I can compute for the best guy from this side and the best guy from this side, the log likelihood of the data. And whoever has the higher log likelihood wins. And then that would be crowned the my learned hypothesis. Looks good, right?
Time.
What?
Time required for the computation.
Yes, there will be time. There will be a lot of time. But at least, it's doable, it looks like. Yes, there's a lot of time involved because it's not like you only have 2 topologies to consider. You have essentially double exponential number of topologies to consider. So one idea you might say is, if I have too many topologies, I'll start with a topology like this. Then consider local moves to the topology. Get a new topology by adding a link or deleting a link. And then recompute the best for that. And so it's like hill climbing. And I'll see what's the best value here, what's the best value after the step. And if this is better, then I stick to this and keep doing local search. That's what I would do. What is interesting is this. If you do this, if you actually compare this guy and this guy, do you know who will win? This guy will always win. Always. A complete network always wins. You can always increase the likelihood of the data by throwing more links into the network, which will allow you to learn even more parameters given the same data. And we'll talk about it as we talk more about learning, that this is essentially a classic overfitting problem. You're essentially picking the parameters here such that it exactly fits the data you have observed. But we argued ourselves that last time around when we saw this, that this is the evil. This is not the kind of thing that I want to learn for this. And yet I'm saying if you do local search, this is where you will turn up. Why? once again, anytime anything goes wrong in maximum likelihood learning, it's because of what's called the, what the Christians say, the birth sin or whatever. So the very beginning of maximum likelihood, we essentially made the sin of saying all hypotheses are equally likely. That means all topologies are also equally likely. If all topologies are equally likely, why are you complaining if I give you this as the best topology? You don't believe what you just said. You essentially want to say that some topologies are more likely than others. And so in some sense, I need to give a penalty for the topology based on how many links it has. And you can think of it either as a penalty or think of it as that just means that has a lower likelihood in the prior, a lower prior probability of that hypothesis. You see what I'm saying? So you go as far as you can with maximum likelihood, but whenever it fails, you will then do stopgap arrangements. We did this for zero counts by throwing in some virtual examples. And you do it here by saying, well, actually, I will add a penalty for each topology based on how complex it is. And from a network point of view, what is complexity? It's just the number of edges. Okay? That way, even though this guy is really, really agreeing with the data, you would say, no, you're not good enough. So this is like your Earth being put in the center. I make a planetary model whose picture looks as big as this room. Because I have to do all sorts of crazy things. You know, on Sundays, in leap years, Venus has to do some sort of a somersault just so that it will agree with the data. I'll make it do it. Okay? It agrees with the data. And then this guy pretty much agrees with most of the data with a little, I mean the solar, sun being in the center agrees with most of the data with a small amount of noise. And so then this guy is about to win the day, the Earth-centric theory is about to win the day, and then you come in and say, hey, Earth-centric theory gets a penalty for being too complicated a hypothesis. And so that's how you equalize the game again. Something we said we won't do, we have to do eventually. Okay? When we go more into machine learning, there is another types of terms for this prior of the hypothesis, also called regularization, which some of you may have heard of, and I will mention it here again. Regularization is again bias over hypothesis. Okay, without a bias, you can't learn, essentially. And so if you have a bias, you have a prior over the hypothesis. And that has to be used in doing search in the topology space. It's a much harder problem than just complete data, clearly, right? Because you have to consider every topology. But it wouldn't even be solvable unless I do a penalty, because otherwise everything will just go here. Some of you who might know k-means, for example, might see that you can do number of clusters by keep increasing the number of clusters and only consider the dissimilarity between clusters. And that if you do that, you'll always wind up picking the number of clusters to be equal to the number of examples. That means every one of you will be in your own cluster. That's no good. And so you have to penalize that clustering. And that's again essentially putting a hypothesis prior. Okay, I'll stop here. Next class, when I come back, I will do a little more about the naive-Bayes classification and expectation maximization, and start talking about machine learning, which is what this is really.